The second lecture of takeoff performance is about the drag. Okay, so this is an aircraft during ground run, and we know in a along the vertical direction, we know there's weight and um, also lift. Although it's during ground run, there's still lift produced by the wing. On the horizontal direction, we have first of all the thrust produced by the engines, and on the other hand, we have the drag, and also because our carriage is still uh, on the ground, so there's friction drag, we use F. So according to the Newton's law, we can write down the governing equation, m times acceleration, so dv over dt equals t thrust minus the drag and friction. Okay, so you see the drag D is highlighted with red, and we will pay special attention to drag now as a topic of the this lecture. And the drag can be divided into parasitic drag and induced drag. So we will discuss these two components separately. The parasitic drag, dP, is a drag results when the object is moving through a fluid. For the aircraft, it's air, and also we can also say it as aerodynamic friction. Okay, so if the airspeed increases, and the drag, because it's relative motion between the aircraft and the air. So if the velocity increases, dP parasitic drag will becomes larger. Now let's go to the induced drag DI. Induced drag is a result of the increasing amount of lift generated during the takeoff ground run. So that's due to lift generation, the induced drag. Okay, so now let's have special attention to the induced drag, and as we said earlier, that's a drag due to lift generation. Okay, so we have the induced drag coefficient here. So CDI equals CL squared divided by pi times E times aspect ratio. And if we replace 1 over pi E aspect ratio by K, so we can simplify this equation to K times CL squared. So this is induced drag and how it relates with lift coefficient. Why lift coefficient? Because we say it's due to the lift generation, so that's why we have CL included. Okay, so we know K equals 1 over pi E times AR aspect ratio, and E is Oswald efficiency number, and so it's a correction factor that represents a change in drag with lift of a 3D wing. So if there's if it's a 3D wing, which is usually the case, so we need to apply this E factor. And AR is an aspect ratio. So aspect ratio is defined by B squared divided by the S. B is a wingspan, S is a wing area. So for rectangular wing, which is most simplified geometry for the wing, so AR can be simplified as B over C, because S is B times C, so the B on up and down are cancelled, and C is the chord of the wing. Okay, so there's also ground effect during the ground run. The ground effect applies to the lift generation and also the induced drag. So what is ground effect? Ground effect is increase of lift and a reduction of induced drag when an airplane is flown at slow speed very near the surface. So usually we take into the ground effect when the aircraft is within the distance between the aircraft and the ground is within a wingspan, so roughly. Okay, so why we have the ground effect? So why when the aircraft is closer to the ground, the lift is increased and the drag is reduced? That's because ground surface obstructs the creation of wingtip vortices and interrupts the downwash behind the wing, which means that wingtip vortices cannot be fully developed, and also the downwash will be destroyed, so won't be able to fully develop. So those adverse effects could not propagate, could not develop, so we receive the benefits. So it's an advantage for the aircraft. Okay, so we have also factors KGE, ground effect. That's a ratio um, between the induced drag coefficient, in ground effect, and out of ground effect. So IG is the in ground effect, OGE is out of ground effect. So CD becomes smaller during ground than the CDI, out of ground effect. And so it's the expression is showing here. I'm not reading it. And on the right hand side, we have a graph. So the horizontal axis is h over b. H is the height of a wing above the ground. B is the wingspan. So when the ratio goes from 0 to zero point 0.8, which means the height increases, so the aircraft is further away from the ground. So which means the KGE should be approaches to 1.0. So which means the CDI, in ground effect and out of ground effect are similar. So you can see once it's closer to 1, the ground effect diminishes. Okay, so when the ratio H over B increases to 1, KG approaches to 1.0, the ground effect uh, will be diminishing. Okay, so just now we discussed the drag, especially the induced drag. In the induced drag, we also talked about the ground effect, how the ground effect affects the induced drag. So we know that's benefit. The induced drag will reduce. Now we'll move to the other component in the governing equation. That's F, the friction drag. So the friction drag is from the rolling on a carriage, and it can be calculated as mu times the difference between W and L. W is a weight, L is a lift. Mu is a coefficient of rolling friction. And so we know if L, the lift, increases, and since the weight W doesn't change, if L increases, the friction drag will reduce. And also, in the same time, the induced drag will increase because induced drag is associated with a lift. So if the lift increases, the induced drag will increase at the same time. Okay, so coefficient of rolling friction, that's mu, can be affected by the runway surface and the wheel slip ratio. So there, I mentioned 2 factors in here, but actually can be affected by much more factors, such as the type of wheel and the type of tire of the aircraft and the wheel diameter and different things. But we are highlighting 2 parameters. That's runway surface and wheel slip ratio. So let's first have a look at the runway surface effect on mu, and we can say there are several different types of the surface material of the runway are listed in here. For example, the concrete, hard tough, different things. And we can see the rolling friction coefficient mu and varies. So if it's concrete, its mu is about 0.02, and there are different numbers. If under braking, mu becomes 0.7, and so that's typical numbers. You can have a look. And now let's have a look at the wheels slip ratio. And we can see this graph. the horizontal axis is the slip ratio. That's from 0 to 1.0. And what's wheel slip ratio? That's if the slip ratio is 0, means um, the wheel is just rolling freely, and if it's 1, means the wheel is locked. Okay, and we can see the mu friction coefficient increases first, and so largest friction happens at slip ratio about zero point 0.2 something, let's say 0.25, and then decreases linearly to when the wheel is fully locked. So we can see the largest friction coefficient happens 0.05, let's say. And that's why um, when we do the brake, if we fully lock the wheel, it doesn't actually produce the largest friction. Okay, so then um, that's the smart way of doing the brake. We have the anti-skid system for not only for aircraft but also for cars. Yeah. Okay, so this is about the frictions during the ground run. We discussed about the induced drag and also the friction drag.